Okay, so moving on to chapter 4, we are going to take everything that we learned in the first 3 chapters and we're going to extend it to even more conceptual spaces. So the first thing in 4.1 we're just going to define is what a vector space and what a subspace is. And we are thinking about basically a set of objects. These could be polynomials, these could be actual vectors we've been working with in the past, these could be more conceptual shapes, something like that. But basically we're going to say that a vector space is a collection of objects, and for our purposes we're not going to use anything too complex, pretty much just going to continue using vectors and polynomials. But the key is they're going to behave like the vectors do in Rn, the vector space, where each vector has n components. And we're going to call each of the objects actually a vector so that it keeps some of our operations that we've been doing a little bit simpler. In order to be a vector space though, one, it has to be a non-empty set of objects. So we can't have just an empty set and say this is a vector space. It has to at least have a certain number of items. And then 2, we need to have 2 operations defined: addition and multiplication by scalars. Okay, that does not mean that vectors need to be multiplied by each other. And you can see that especially if we would say that anything we've been working with, like R3, would not be a vector space because we could not multiply something like x1, x2, x3 by something else like a1, a2, a3. Even though these 2 vectors are both in R3, we couldn't multiply them by each other. So a vector space does not need to be multiplied under vector addition, but it does need to be defined under not vector addition, vector multiplication. It does need to be defined with scalar multiplication. So I can scale each of these vectors to continue, and I could add them together. So in order to prove that something is a vector space, we actually have to prove 10 different axioms. I'm not going to ask you to prove all 10, but some of them are pretty important. And if you have printed the notes that were on Google Classroom, I made a typo right here. This on Google Classroom used to say u plus v equals u plus u. This is just supposed to represent the commutative property. So what each of these axioms means is that if I add 2 vectors together, the result will still be in the vector space. The commutative property holds. The associative property holds. There has to be a 0 vector, and the 0 vector is actually defined in a very specific way. It's not necessarily 0, but when I add, we think about it as being the additive identity. So if I add it to another vector, the vector does not change. So that's how we're going to prove that the 0 vector is in a different space. There's also an additive inverse here, where if you add them together, you add something and its additive inverse together, you get 0. If you multiply by a scalar, you also get a vector that's in the vector space. The distributive property holds both with scalars and with vectors. Notice that this is a vector to 2 scalars being multiplied together, and this is a scalar being multiplied to 2 vectors here. Again, associative property of multiplication. I don't know why this is still here. And finally, the multiplicative identity, where I multiply by 1. So in order to be a vector space, all 10 of these things need to be true. So basically, anything that we've been dealing with up until this point has been a vector space. So really common ones are just the set of all real numbers, the xy plane, 3-dimensional Euclidean space, or any Rn that we've been working with vectors. We can also have complex vector spaces. We are not going to go in depth about complex vector spaces. We're going to stick to the real vector spaces. But just to let you know that that is still a thing, something you could be asked to learn about future in college. So important fact is that the simplest of all vector spaces is still the 0 vector. Okay, the 0 vector is kind of special. It's a non-empty set because it does contain the 0 vector, and all 10 of these properties up here will hold for just that vector. So let's do a couple of examples working with different important vector spaces. So thinking about here a set of quote-unquote vectors that are actually matrices, 2x2 matrices, where all 4 components are real numbers. Here, let's take a look at how I would prove that the 0 vector is in this space. So what I'm asking is there a vector such that when I add it to M, I get M out? and it has to fit these conditions. Luckily, this is pretty simple. We can make a 0 vector by making a matrix of all zeros, and that fits the conditions for this vector space because each of those entries is a real number. 0 is a real number. Okay, so this will be the 0 vector in this vector space, okay, which is actually just all matrices. And then another special one that we're going to use throughout this chapter is a set of polynomials. So we are going to let P sub n be a set of all polynomials of at most degree n, which has to be greater than or equal to 0. Okay, so they look like this here, which looks exactly like something we did last year. And I don't mean multi, I do mean BC calculus. They look like the Maclaurin polynomials. Okay, but I mean, you could also say that they look like any polynomial in general. But we are using t. All of the coefficients are real numbers, and t has to be a real variable. We are going to go ahead and look at some of how to prove the axioms of polynomials like this on the next page. I'm not going to prove all 10, but we'll look at a couple. And I typed it out for you here just so we can start to get to how I want you to prove some of these things if we are asked to prove that. And the important note here, you must define each by component. Okay, so I defined 2 polynomials here because we are going to look at adding to, and remember this is technically what we're considering a vector, and this is technically what we're considering a vector, an object in this space, and we're going to add these 2 things together in some of these. So when I add, it should be that when I add the 2 vectors together, I should get another polynomial that fits this format. So if I think about combining like terms based on coefficient, or excuse me, based on the degree next to them, I would be adding the constants together. That would be a naught and b naught here. And then I would add the coefficients of t together, so that's a1 and b1, and keep on going until I reached an plus bn. But this is another polynomial with just bigger, or maybe smaller, maybe if one of them was negative or something like that, with bigger coefficients. So this is also a polynomial. We didn't change the degree, polynomial, at all by addition, so it's still of degree at most n. This addition still follows our vector addition rules. And we want to look at the 0 vector, axiom 4, is the 0 vector in this vector space. So we must prove that by showing that if I add a polynomial of zeros, so basically a polynomial where all the coefficients are zeros, to another polynomial in the space, I will get p, that polynomial, back out. And so when I add 0 to a naught, 0 to a1, 0 to an, all the way down, I just get, nothing changes, nothing about the coefficients changes, so I get another polynomial, actually the same polynomial I began with, the same one up here. Okay, so yes, this additive identity, this 0 vector does exist in this space. And finally, we'll look at if I multiply a polynomial or a vector in this space by a constant, what happens? Is that still a polynomial that follows these rules? And so I distribute the constant to each term. So I'm getting c a naught plus c a1 times t, blah, 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 all the way down to c a n t to the n, which again is another polynomial of at most degree n still in this space. Okay. Okay, notice that this polynomial vector space would not be defined under polynomial or vector multiplication, because if I multiplied 2 polynomials together, the degree would increase and probably be over the degree of n. So that would not, multiplying p times q would result in a vector or a polynomial that is not a part of this set. So that is why most vector spaces are not defined, or well, all vector spaces are not defined under vector multiplication. Okay, but important thing about these proofs is I broke them down each by component. We didn't stop here and say like, yep, that's true, that's in the nth degree polynomials. So we need to look a little bit closer though, because there are some spaces inside of vector spaces that are more important for us to prove, and they're easier to prove, which is really where we're going. We are going to call these a subspace. So one, we have a big vector space, just a set of items that kind of follows all of the math rules we've been using since elementary school. And a vector space is a smaller set of objects inside that space. So think about like a big diagram. So this would be a vector space. Oh, yeah. And then inside somehow would be a subspace. In order for something to be a subspace, kind of an inner set of objects to be a subspace, we have to have three conditions. One, the zero vector is a part of that set. Two, if we multiply a vector by a scalar, we get another vector in the same plane, or well, another vector in the same space. And two, if we add two of the vectors in the subspace together, we get another vector that's still in the subspace. So we call these, instead of having this be defined, we want to say that these are kind of closed over these operations. So to prove that something is a subspace, three conditions. And I gave you this example here as a plane in R3. As long as that plane goes through the origin, then combining vectors in that plane or scaling vectors in that plane will still make the vectors in the plane. It won't send us outside the plane. So that would be considered a subspace. Okay, but to prove it, one, we need to prove that the zero vector is in the subspace. Here I'm using V as the vector space and H as the subspace. Two, for each U and V, again, if we add them together, that sum is still in the subspace, closed under vector addition. Okay, and then again, for each U already in the subspace and a scalar, a constant, C, if I multiply that vector by that constant, it will still be in the subspace, so closed under scalar multiplication. Okay, once again, just like the empty set was not a vector space, the empty set is still not a subspace because it doesn't even follow the first condition, which was that the zero vector is still in that space. But the smallest subspace is again just the zero vector all by itself. Adding 0 plus 0 will give you 0, so that is still in the subspace, so it's closed under vector addition. Multiplying 0 by a constant will still give you 0, which is again still in the subspace. And then if the zero vector is the only thing in the subspace, obviously the first condition is met. The zero vector is in that subspace. But let's go ahead and let's look at some other, how to prove that other things are either subspaces or not. So we'll do two examples. One in which this is a subspace. Oh, let's focus. There we go. Okay. All right, so the easiest thing to check is that the zero vector is in this space. So let's define what this subspace is first. We've set some conditions here. H, representing the subspace, is a set of all three-dimensional vectors where it has a 0 in the middle, and then the top and bottom are just real numbers. That's all that's required for a vector to be in this subspace. And we want to show that it is a subspace. So 1 is the zero vector in this subspace, okay? Which means, again, if I have, let's say U is in H, I want to add U plus 0 will give me U. That's the property that I'm looking for. So I have A and B are real numbers, and then I will let specific ones, A1 and B1, both be 0. Okay, that's how I will define my new vector. Then a vector, oh, I'm writing really big, I should write smaller, A0B, which fits the conditions given here, plus the vector A1, 0, B1. Okay, that's really A0B plus 0, 0, 0 will equal wow, that was bad. A0B, which is still in H. That the format of this vector still follows the conditions that were set out here. So we know that this sum, a vector plus the 0 vector, is still in the subspace. Okay, therefore, the 0 vector is in H. So condition 1 met. Condition 2, okay, I'm going to set two vectors, so let U equal A1, 0, B1. And we're kind of forgetting about what I did in step 1. And we're just defining some new vectors. So V is A2, 0, B2. Okay. For A1, B1, A2, B2 that are real numbers, when I add U and V together, I get A1 plus A2, 0 plus 0, and B1 plus B2, which is, once again, still in the vector space. That still is a real number, 0, and a real number. That fits the conditions set out here. Okay, therefore, H is closed under vector addition. And we need to check one more thing, and that is that it's closed under scalar multiplication. So I'm letting there be a real scalar. C is a real number. And U, again, is the vector, let's just say A0B. Let's not even say A1. Okay. C times U will be C times A, C times 0, which is 0, and C times B, which is still in the vector space H. It still is a real number, 0, real number. That fits our format given up here. So therefore, H is closed under scalar multiplication. Okay, final conclusion statement. All three conditions have been met. Therefore, H is a subspace, and we want to say what it's a subspace of. R3. Okay, QED. And you're thinking, that seems really simple. I feel like this will happen all the time. Well, let's take a look at example 4. So notice that the conditions for this supposed subspace, that we're going to prove whether or not it is a subspace, is that we have two components, so we're in R2, and that the first component is a number that we choose, a real number, and the second component is one more than that number. So the first thing we're again going to check is if the 0 vector is in this subspace. So it will be that we could have x and x plus 1. We could add the 0 vector, the two-dimensional 0 vector, and get x plus 1. But to create the 0 vector, it doesn't exactly fit the format. We would have to have that x equals 0, but we can't have that happen at the same time that x plus 1 equals 0. I don't know why that put plus or minus. That can't happen for the same x. Okay, so 0 vector is not in H. Okay, therefore H is not a subspace. So this goes to show you that even though something has the right kind of format for having a 0 vector, it looks like we could create, like, okay, I put a 0 here and a 0 here. That's a 0 vector. But that vector itself doesn't follow the restrictions I've been given here, where the first entry had to be a number and the second entry had to be one more than that number. So we want to make sure that whenever we are proving things, all three conditions, that every time we add or subtract or multiply, it's still, we either end up with a vector that fits these conditions, or the vector we added or subtracted also fits the conditions, because we can't add or subtract anything that's not already in this space. Okay. All right, one other shortcut, kind of nice. I'm not going to write it up, but we'll talk through it together. So in case you need to pause at any point. Okay. So let's see if this will refocus. There we go. Okay. So our theorem says that if I have some vectors that are in a vector space, then the span of those vectors is a subspace. This is kind of tying it all back to what we've been doing. Again, remember the span is the set of linear combinations of these vectors. So we're going to do a quick proof. And the idea is that for a vector, x, to be in the span of v1 through however many vectors we have, vp, that means that x is a linear combination of v1, v2, all the way up to vp. And these a1, a2, ap are all constants. So first we're checking the zero vector. In order for the zero vector to be created in this space, we can just let all of the constants be equal to 0. Okay? And that means x will be the zero vector, which would be a linear combination of v1, v2, vp, where all the weights are 0. That's the zero vector. Okay? And if I added that to any of the vectors that were in this space, I would get the same thing. I would get, if I added x to v1, I would get v1. Okay, so the zero vectors in the span. If I add two vectors, so I'm letting y be in the span and another vector z be in the span, then y plus z, and this is a linear, this right here is what I'm calling the linear combinations that equal y, and here I'm letting this be the linear combinations that equal z. Then if I just combine like terms, I'm getting another linear combination of all the vectors v1 through vp, where I've just got bigger constants or bigger weights next to them. That's still a linear combination of those vectors. That's again in the span, so our span is closed under vector addition. And then finally, I think this one makes the most sense to us, but if I have a real number, c, and I multiply a vector y that's already in the span by that constant, I'm just getting another vector, another vector that's in that span. Because I've just scaled each of the constants. It doesn't change the fact that it's still a linear combination of the vectors that made up the span. So the span 1 has a zero vector in it. 2, if I add two vectors from the span together, I get another vector in the span, just another linear combination. And 3, if I multiply a vector that's in the span by a constant, I get another vector in the span because I just scaled a vector that was already a linear combination. So because of these three conditions, the span of any set of vectors that are in a vector space, okay, so they have to be in a vector space first, that kind of is a given. We've been using the fact that we are using vectors in a vector space to be able to have all of these operations be defined. So assuming that these vectors are in a vector space, the span of those vectors is also a subspace of V. So, that was a lot of little proving things. So this is definitely going to be a conceptual chapter, but what we did this time, and these will be posted on Google Classroom, I have some more examples in here for you to keep proving if things are subspaces. So one, we defined what a vector space was. A vector space is a set of objects. They could be vectors, which is what we've been dealing with. Here's my typo. But it also could be something like polynomials or other items. The simplest ones are just the multi-dimensional sets we've been using. They have to be defined for 10 different operations, but those are the operations we've been using since we kind of started learning math. What's more interesting though is us proving, and if you are proving something, you need to split it up by component. What's more interesting though is proving that something within a vector space is a subspace. And in order to do that, I need 3 conditions to be true. I need the zero vector to be in that subspace. If I add 2 vectors that are in this subspace, they should equal something that's also in the subspace that still fits the conditions. And finally, it's closed under scalar multiplication. If I multiply a vector in the space by a scalar, the result will still be in the subspace. It will still fit the conditions that were met. Okay? We have a guest appearance.
Is this the camera?
Yeah.
Okay, hey guys, this is Ms. Kelly. Thank you for listening to the 4 whatever notes. I know this doesn't completely replace me, but
Wow, this is rude.
Wait, did I see it? Oh my God, I see myself. Hi guys, this is Ms. Kelly.
I suddenly got
come
way more
before
tan.
school, cougar time, after school. You can remind me whenever you want. The office hours don't really apply.
Wow.
Bye.
Bye.